Many of us have grown up with the idea that Earth simply revolves around the Sun, which stays still in space. But in reality, the big picture is much more complicated and fascinating. As we delve deeper into how Earth actually moves through the galaxy, we'll find that our planet not only revolves around the Sun, but is dashing through space at an incredible speed at the same time, along with our entire solar system. But what if we told you that this movement could be connected to some of the universe's greatest mysteries? For instance, scientific hypotheses suggest that Earth's movement through the galaxy may expose us to cosmic rays, which could cause genetic mutations and contribute to mass extinctions. Furthermore, changes in our planet's orbit around the Sun may affect the environment, potentially leading to catastrophic changes like another ice age. Understanding how our planet moves through the universe allows us to appreciate our place and space more. We may even find clues to answer some of the bigger questions, such as how our galaxy formed and what the future holds for us. For starters, imagine that you're in an airplane that's flying at a constant speed and altitude. While inside the plane, you won't be able to tell how fast you're going or if you're moving at all. From your point of view, it seems that only the world outside is moving. However, someone on the ground watching a passing airplane will perceive its movement relative to their own stationary position. This concept, known as Galilean relativity or Galilean invariance, was first outlined by Galileo Galilei in his 1632 book, The Dialogue Concerning the Two Chief World Systems. Galilean relativity defines the absence of an absolute frame of reference for motion. Even when there are several valid frames of reference, we still need to choose the most relevant one depending on the situation. So how does this fit in with the idea of Earth's movement and the solar system as a whole? First, we need to determine the observation point. When viewed from within our star system, we all know that the planets orbit the Sun. However, with a broader consideration of things, we can see a completely different picture. The solar system is constantly moving in a spiral through the expanse of our galaxy. One of the best-known examples of relative motion within our solar system is Earth's revolution around the Sun. Earth's orbit is not a perfect circle, but rather an ellipse, with the Sun as one of its foci. That means that at some points in its orbit, Earth is closer to the Sun than at others. When Earth is closest to the Sun, it is said to be at perihelion, and the farthest point in its orbit from the Sun is known as aphelion. These 2 points occur at regular intervals. Earth reaches perihelion around January 3rd and aphelion around July 4th, which is evident with the seasonal changes in weather. The usual depiction of the solar system, with the Sun at the center and the planets revolving around it, is not a completely accurate representation of the solar system. The movement within our planetary system is complex. The planets not only revolve around the Sun, but also pull it in, causing it to shift. For example, gas giants like Jupiter and Saturn have a strong gravitational influence on the Sun and Earth, resulting in small changes in the shape and orientation of their orbits. When Jupiter and Saturn are aligned, they have a significant effect on all bodies in the solar system, known as the perturbation of the outer planets. Over time, these subtle changes in Earth's orbit can accumulate and lead to long-term changes in the planet's climate and environment, known as Milankovitch cycles. One aspect of these cycles is the change in the tilt of Earth's axis, which occurs in a cycle of about 41,000 years, shifting from about 22 to 24.5 degrees. This change in tilt affects the amount of solar radiation reaching different parts of the Earth's surface and can impact the timing and intensity of glaciation periods. However, it's important to note that currently, the effects of anthropogenic climate change are suppressing Earth's natural climate cycles, making it difficult to predict the exact timing and intensity of future ice ages. Now, let's consider Earth's movement through the Milky Way galaxy. The galaxy is a massive and complex system spanning over 100,000 light-years in diameter, consisting of stars, gas, and dust. The Milky Way rotates, with its spiral arms trailing along as it spins. Earth is located in one of these spiral arms, about 25,000 light-years from the galactic center. In the solar system, The Sun is the dominant celestial body in terms of gravity. However, in the Milky Way's gravitational field, there is no dominant object. Everything revolves within the total gravitational fields of everything else, which makes tracking the motion of the galaxy's components a challenging but rewarding task for astronomers. Just as Earth orbits the Sun revolves around the center of the Milky Way galaxy at a speed of about 143 miles per second, completing one orbit in almost 230 million years. Interestingly, the stars in the inner regions of the galaxy move faster than those in the outer regions due to the higher mass closer to the galactic center, resulting in a stronger gravitational pull. This difference in speed is similar to how planets closer to the Sun move faster along their orbits than those farther away. Determining the speed of the Sun relative to the galactic center involves observing new young stars and studying their motion. On average, the Sun drifts forward at a speed of about 3.1 miles per second towards the galactic center and moves up and out of the galactic disk at about 4.4 miles per second. This small peculiar motion has significant implications for the path that the Sun and our solar system take within the Milky Way. The orbit of the Sun around the center of the galaxy is not perfectly circular. Instead, it follows a slightly elliptical path oscillating above and below the galactic plane. This movement is influenced by the gravitational pull of other stars, gas clouds, and dark matter in the galaxy. We are currently several dozen light years above the middle plane of the galactic disk. Although it's difficult to determine exactly where the center is, since there is more matter below us than above us, the gravity of the disk slows our upward movement. In a few million years, we will be about 300 light years above the center of the disk before our upward movement slows to a complete halt and we begin to descend. The vertical oscillation of Earth has more significance than just being a peculiar phenomenon. Some astronomers support the Shiba hypothesis, which suggests that it can be directly related to mass extinctions on Earth. The center of the disk is considered a more dangerous place for the solar system due to the higher density of stars and the radiation they emit. The motion of the galaxy's spiral arms is not yet fully understood, but is theorized to be caused by a combination of factors. One of these factors is the gravity of other galaxies in the local group, which includes the Milky Way. Another factor is the existence of density waves, which propagate across the galactic disk like ripples in a pond. These waves can force stars and gas in and out of the spiral arms, potentially affecting the environment and living conditions on Earth as we pass through these regions. For example, as the Earth passes through an area of higher density, there may be more cosmic rays and other high-energy particles reaching the surface of our planet, which could have implications for our climate, atmospheric chemistry, and even the evolution of life on Earth. The Sun is not stationary. It moves through the Milky Way galaxy, dragging Earth and the other planets along with it. However, the Sun is not the only moving object. All other stars in the galaxy are also in motion. The motion of stars can be defined in terms of their proper motion, which refers to the star's visible motion across the sky over time. Proper motion is caused by the movement of stars in space relative to the Sun. It is usually measured in arc-seconds per year, which is the angular displacement of a star in the sky over the course of a year. Proper motion allows astronomers to track the movement of stars over time and study their movement and position relative to each other. This is important for understanding the structure and dynamics of the Milky Way. Earth's movement affects our perception of the night sky through parallax and the proper motion of nearby stars. Parallax allows astronomers to determine the distance to nearby stars, while proper motion results in changes in the positions and constellation patterns of stars over time. In addition, our solar system is not only part of the Milky Way galaxy, but also the local group, which is moving towards the Great Attractor at a speed of 373 miles per second. The entire universe is also expanding, causing galaxies to move away from each other. Earth and our solar system are moving through the universe at about 229 miles per second relative to the cosmic microwave background radiation. In summary, Earth's movement is dynamic, encompassing various celestial motions within the solar system galaxy, and the expanding universe.